Okay, it's 11:30. It is my great pleasure to introduce Jake Howard, who is going to give a talk entitled Halt and Catch Fire, Forcibly Stopping Python. Could we give him a big round of applause, please?
Wow, I had reckoners. I don't think I have them anymore. Yes, so as the slide says, I'm Jake, and I'm going to be talking about stopping your Python code. So a little about me. Who is this bloke who's going to be standing and talking to you for the next 20 minutes? I'm Jake. I'm a senior systems engineer at Torchbox. I'm also on the security team for the Django Web Framework and a member of the Django Software Foundation. I do a fair bit as well with the Wagtail CMS because I work at Torchbox and amongst other reasons. And all of this means I do a lot of very weird things that are vaguely related to technology, which hopefully explains what you're about to hear about. So code is meant to run. As software engineers, we write code that is meant to do stuff. Most of the time, what we tell it to, hopefully, it starts, it does its thing, and then usually it stops. Usually the code runs until it's done, i.e. it runs out of stuff that we have told it to do. But what about when that doesn't go according to plan? What if we need it to stop sooner? Well, the quickest and easiest way to do that is to go up to the machine that is running your code and hoik the power cable out of it. Computers can't run if they don't have all those magical electrons to do things. But you probably want something slightly more graceful than that, and probably something you can include into your projects. I am never going to let Gunnercorn talk to the UPS on my servers, because otherwise we will get actual fires if something like that does try and happen. So what if we want to stop our code sooner than intended? Well, not just when it says it's done, when we say it's done. Something slightly more graceful than yanking out the power cable. Well, some APIs already have the concept of timeouts. If it takes too long, it raises an exception for you to handle and deal with. If an API supports a timeout, you probably should be using it, even if it is slightly defensively. However, they only work where they're implemented, which isn't for everything, and usually only for what looks like a single statement or operation, such as making an HTTP web request. For everything else, we can raise exceptions ourselves. We can stop the code where it is and return control to the parent. Usually we'll do this ourselves with a raise statement. Sometimes it's Python telling us we're doing something wrong. Other times it's the fact that we can't actually divide by 0 no matter how hard we try. And other times it's the operating system trying to tell us something, which Python then helpfully converts into an exception for us. So to add a little bit of context, I'm building a task queue for Django. If anyone has heard of the Django Tasks project, that's me. If you're thinking about this being the competing standards XKCD, you are hopefully wrong. The basics are all going well, and actually just as of Tuesday this week, the core was actually merged into the main branch for Django 6.0, which is fantastic. But there are still more features that I need to work out how to write. I need to be able to make them reliable, cross-platform, and not make the code reviewers cower in horror. A common feature for task queues is being able to set a timeout for a task. If your task is meant to take 10 seconds and it ends up still running 10 minutes later, something has clearly gone wrong. Setting a timeout is a really easy way to prevent this and to alert you when that does actually happen, so long as you have some form of alerting. The task needs to either have finished naturally within the time limit or be told to stop by its parent. But the tasks themselves, they're not mine. Someone else has written that. There's no telling what's going on in there. And we can't make assumptions about how it works or really impose any restrictions on it. So with a task queue, or most supervisory code, as it were, there's generally two bits you're trying to deal with. First, we've got the supervisor. This is sort of the background worker itself, the bit I need to build. This is generally what happens, what keeps an eye on the inner parts of the code, and then is also what tells it to start. And if the inner code has problems, control flow returns back up. And then, of course, we've got the code itself, the task that someone wants to run. Generally, it'll be a function with a bunch of metadata bolted onto it. The fewer assumptions that the supervisor makes, the more flexible that the inner code itself can be, but the more complex that supervisor needs to be, and the more work I need to deal with. So I know kind of what I want. If a function takes too long, it stops with some magic. If not, it runs as normal. But now I need to actually build the damn thing. And that is kind of what most engineering is. And with most engineering problems, there are many different ways to do it. If we were in a perfect world, maybe the inner code can actually work with us. Perhaps the inner code can simply just check if it is time to stop. Rather than us needing to step in, it can be a slightly more cooperative relationship. If it's time to stop, the code just stops. This would be great. This pattern is especially useful when polling or doing small bits of work. You do a piece of work, and then you check it's time to stop. But sadly, we don't live in a perfect world. Wouldn't life be so great if we did? I can't make assumptions about what's running in there. It's just a function which does stuff. If the inner code never actually checks for that cancellation token, it'll never stop, even if it is actually asked nicely. Even then, if you do need to the action promptly, frequent checking may not even be good enough. If a loop takes 2 seconds, then it would take nearly that long for the code to even actually stop. And if there aren't natural breakpoints, it's not something you can shoehorn particularly easily in your code, for example, with what the notify user method would have looked like. Building some context, rendering a template, and then sending an email. You can try and shoehorn in some breakpoints, but it just kind of looks horrible. So unfortunately, we can't be nice about this. We do need to be a little bit more forceful. So if we can't rely on the inner code being nice, we need to interrupt it, force its hand a little bit. And in Python, the way that is done generally is with exceptions. Exceptions are Python's way of interrupting us, changing the flow of the application, usually to signify an error. They alert us when something is wrong and allow us to take corrective action. Sometimes we might expect these errors, other times we're doing it slightly more defensively. The inner code can raise an exception, and then the control flow trickles back to the supervisor or whatever is catching the given exception, or right back up to the top of the program. And this is exactly what we want. Better still, they're a well-understood part of Python. You can rely on them for your production-grade applications. You let control flow go back to the supervisor without too much hassle, and it's a lot better than those weird go-to implementations that exist. Don't look them up. They do exist. Usually, part of the code decides that something catastrophic has happened and then needs to raise an exception to be handled. However, exceptions work from the most inner code and work their way up the call stack. And that's the complete opposite of what I need. The inner code doesn't decide when to stop, we tell it when to stop. The supervisor can't just raise an exception inside a different function, right? Well, I kind of need a way for the supervisor to wait a given amount of time and then raise an exception so the control flow can go back to it stopping the inner code. And that's really the core of the problem. So we need Python to be able to do 2 things at once. We need it to be running the task itself, and we need it to raise an exception after a timeout, keeping an eye on that task. My partner tells me I'm terrible at doing 2 things at once, so how am I meant to teach a computer to do the same thing? Well, cheaply running code in parallel, well, that sounds like threads to me, global interpreter lock aside. The threading API is actually fairly simple to achieve what we want. Start a thread, wait some time, and then throw an exception. Easy. Well, this might look ideal, but it doesn't actually work. It'd be a really short and boring talk if that's all it took. The exception is thrown in the thread, which is great, but it stays in the thread. The thread stops, but the rest of the program keeps going, unaware of what's gone on. Python even prints the exception stack trace to taunt us a bit of the fact that it's not going to let everything return back. So back to the drawing board, the talk continues. Well, what if we flip things a little bit? We run the inner code inside the thread, and then just stop the thread when the time comes. Well, that doesn't work either. Again, I'm not that lucky. The internet is littered with people asking, how do I kill a thread? And the short answer is basically, you can't. Well, you can, but there's a long answer. But basically, the API doesn't exist. You can't, for the purposes of this talk. The best answers usually talk about having some kind of cancellation token for the thread to check to then actually terminate gracefully. But at that point, we're back at the issues with cooperative cancellations and making assumptions about that inner code, which, again, I can't do. There we go. So, doing it with vanilla threads is clearly off the table. Well, what if instead we actually let the operating system do it for us? The OS already has its own ways of telling us when we're doing something wrong and that we need to stop. Signals are a way for the operating system to communicate with a process and to give it basic instructions. It's not a fancy communication bus, it's basically a magic number. There's sort of multiple different intensities of the word stop. You've got things for bad memory references, even changing the size of the terminal is actually a signal. Perhaps we can borrow some of these methods to our advantage, sort of bend it to our will. Well, if you run some code when your program receives a terminal, you register a handler. Then Python will run that function when the signal is received, so you can handle it however you like, or in some cases ignore it entirely if you like. But crucially, the handlers are not actually run in a different thread like you might think. It's the same thread. Python just interrupts us and changes context, runs the handler, and then changes back. Well, that sounds a lot like what we want. So from a thread, we can send ourselves a signal in a given amount of time, catch the signal, and throw an exception. And that exception is running in the current thread, which is great. And for the first time in this presentation, that actually works. It's basically the same as pressing Control-C to stop our application, but with a couple of extra caveats. But we can make this even better. Rather using the previous user1 signal, this uses SIG-alarm. SIG-alarm is a special signal designed entirely for sending alarms to programs after a certain amount of time has passed. Lucky me. And so it even comes with a timer that we can borrow, which is handled conveniently by the kernel, so there's no process overhead nor an extra thread to deal with. Here we can set an alarm for 30 seconds, let the handler raise an exception, and then the default behavior, unfortunately, for a SIG alarm is to hard kill the process, which is why we do still need a handler. But sadly, this solution isn't as perfect as it first seems, and going back, nor is the one that uses SIG user 1, unfortunately. The first issue is with using SIG user 1. SIG user 1 and SIG user 2 are user-defined signals, and we can use them for whatever we like. But the problem is they're Unix specific. They don't exist on Windows. Even our beloved SIG alarm is Unix only, so no Windows support there, and I need Windows support. Secondly, we're overriding a signal handler. Not a huge problem for user signals, but with other signals, we could break other expected functionality. If we override the SIG-int signal, then suddenly we can't control-C our application. Maybe we borrow SIG-winch instead, and suddenly our terminal doesn't resize properly. Or maybe it's functionality in a framework we're using that we're expecting instead. Windows actually has surprisingly few signals, and they're all fairly important. There isn't the spare ones we can just override and steal. And then finally, good old threading comes back to bite us. There can only be one signal handler for a given process, which means that if you need to do a timeout in multiple threads, you sort of can't. And it'll only raise an exception in the main thread anyway. So many of the issues I've mentioned are because we're trying to do this all inside the same process for the supervisor and for the inner code. Threads are all part of the same process, and signals all get handled by that same process. Well, what if we didn't do it that way? What if the inner code was actually an entirely separate process? We can just terminate it like we would any other program. No need to override signals, we can just use the defaults, and there's no additional threads. There's no weirdness going on here. This is all native behaviors and APIs, but unfortunately, it also has issues. For starters, there's the performance of it. Starting an entire process just to call a function isn't cheap. If it's going to be running for a while, it might be worth it, and you can get around some of it with pooling. And you might even see some of that isolation as a benefit, but it isn't always. Different platforms handle starting processes slightly differently as well. Some will take an entire copy of the process and just fork when stuff happens. Others will spin up entirely new ones, and that's something you have to kind of deal with. Some resources as well can't easily be shared between processes, and so can't reasonably be passed in as parameters, database connections, locks, file handlers, stuff like that. You probably shouldn't be passing them between anyway, but you also can't. And killing a process isn't always clean. Resources might not be cleaned up, and deadlocks become a heck of a lot more likely. So when I set out on this task, pun not intended, I wanted something production grade. I wanted something stable, easy to maintain, and ideally pretty testable. Threads, signals, and processes are all really common APIs in systems programming and in the standard library. They're well documented, they're well understood, and they're well tested. Our program is made up of a few layers. On top of the operating system, there is the process. Inside that is where our supervisor code runs and any child processes would run. In reality, there's a little bit of extra layer in between our code and the operating system, the CPython interpreter, or if it's actually CPython. This facades a few things between the OS and our Python code to make our lives that little bit easier. But what if we could abuse that relationship a little bit? What if the interpreter let us do things we wouldn't normally be able to do? As mentioned, it's not possible to kill a thread, but we've already seen the interpreter receives operating events and just magically creates exceptions out of them. Well, what if it was nice enough to magically create an exception for us out of thin air just because we asked it nicely? What if we let the interpreter do all of this for us? As mentioned, it's not possible to kill a thread. That's some duplicated notes. Let's skip that. As it turns out, there is actually an internal API to do exactly this, asynchronously raise an exception inside a thread. It's technically stable if you squinted it hard enough, although it does come with plenty of big red warnings. It takes a thread ID and an exception class and raises the exception in the given thread as if by magic, at the earliest possible point. More on that later. Because it's internal to Python, it is fully cross-platform. And it is CPython specific, unfortunately, for all three of the Python users that are out there. But that's an exception that's a restriction I'm willing to accept. So what does this magical API look like? Well, it's only a few lines, but it's not the most readable. If you're not familiar with the C API internals anyway, but that's nothing a few comments can't solve, right? So let's break this down a little. Well, first we need to create a threading timer for about 30 seconds or so. This is a much nicer way of spinning up a thread, sleeping, and then doing a thing, and it's all built in as well. It's much cleaner to read, but it is functionally identical to what I was showing earlier. This timer has a target of our do timeout function, and it takes a single argument, the ID of the thread that we would like to raise an exception in. We use this little current thread helper to get the main thread's ID, which here is the main thread rather than the thread that the timer spins up. And then finally, the rest of the owl. We need to call the magic method, this py_thread_state underscore set async except. What a lovely thing that rolls off the tongue. If I stumble with my words, that's why. We need to call that with the thread ID and the exception class it should raise. The thread then magically raises an exception as if out of nowhere. Fantastic. Have we found peak timeout? Is this the perfect way of killing a task that is taking so long? Well, it's cross-platform, it's stable, and it probably isn't going anywhere soon, hopefully. And it's still just a small timer thread. So the overhead is pretty low. Well, have we found peak timeout? Well, almost. It's almost perfect. And in fact, it's so close to perfect, it's almost annoying. If you tried to run this yourself, as like running it in a terminal, it'll probably work. You go, oh, this is great. And then you'll try and deploy it into production and realize all these caveats. This works really well whenever Python is being executed, which might not sound bad, but a lot of your Python program isn't actually Python. There's quite a lot of C going on under the hood when you step into like the interpreter internals, which is exactly the problem. If you're waiting for a network response, doing a large matrix operation with NumPy or image manipulation with Pillow, the exception won't trigger because that's all happening inside C. The timeout will expire, set async exec will be called, and just nothing will happen. The task will keep running. The next time that control flow moves back to Python, then the exception will be raised, but that's way too late. Chances are that's not what you'll want. If your code is taking a while, it's probably not the Python part of it that's taking a while. It'll be something I/O related or happening in a separate library. If it isn't that way, lucky you. But I suspect that's an exception rather than the norm. And then, of course, we have good old async I/O. This API, again, here is almost perfect. And better still, it's built in with none of these weird C API internal things. There's a context manager, and if it doesn't exit in time, it raises an exception. If it is fast, the exception never fires. And this is basically the perfect API, the API I want. But of course, life giveth and life taketh away. The problem here is exactly in its features, and it's written very obviously on the screen. It's async I/O itself. It requires everything to be async. If your code is already async, lucky you. But not everything in the standard library is, and not every API that you might be using is as well. And that async I/O slowly will spread over your code base like some kind of pleasant infection. The inner code has to repeatedly yield as well for that timeout to trigger. If you're stuck doing something CPU intensive, like for example calling the wrong sleep function, it won't actually do anything until the next time it awaits, and then it'll go, oh, time has passed, please stop. That's not really what we want either. Which again comes back to assumptions. If I wanted to restrict users to only using async functions, my life would be so much simpler. But many people, especially those using Django, aren't writing very much async code. And so for the sake of compatibility, I can't just turn my back on those users. And I wouldn't really be able to come up to Manchester and talk to all of you about it either. So I've just been through a few different ways of implementing timeouts, each with different trade-offs for portability, flexibility, and performance. Cooperative cancellation is great, it's clean, it's easy to read, and the exit is clean. But both the supervisor and the child need to be aware of it and understand that it might seem perfect, but it's not. Operating system signals, they work great if it's the only thing your process is doing, but it probably isn't. There aren't really any good cross-platform signals to use, and chances are if you do find one, it'll probably break something else. SIG-alarm has all the drawbacks of operating system signals, since it is one, but it doesn't require a timer in our thread, which is a small benefit, I guess. It won't break existing functionality because we're using it for what it's designed for. But again, that's Unix only, Windows users, sorry. Processes, they're resource intensive to start up and manage, and you have to consider what you're passing between that process boundary. There are complexities about how those processes are spawned, and you need to be more careful about state timeout. But you get a really nice resource isolation if you do want to lean on that. Set async exec is almost perfect, but it doesn't work if your code is running outside of Python, and it might raise some eyebrows if you do try and commit it into a code base. And then you have async IO. Async IO, it's got native timeouts, but it requires everything to be async. And it still only works if your task yields frequently enough. It's like cooperative cancellation with a bit of syntactic sugar in the language itself. And as with everything, which one is the best depends exactly on your use case. The more control you have over the system, the better you can optimize your use case. In the case of a generic task manager, the less control you take, the more useful it will be, which is exactly my problem. You might be able to combine some of these depending on your use case. You might be able to switch things depending on the environment or use case, or better yet even, in my case, let the users decide a little bit. For example, Celery, a very popular Python background queuing library, uses a mixture of child process and a bit of native pooling depending on how you configure it. RQ, another one based on Redis, uses either SIG-alarm or the magical set async exec depending on the operating system you're on. Me, personally, I'm erring towards process pools. You get maximum control with fewer surprises, and that's what you want in a production code base. Potentially maybe letting the user lean towards SIG-alarm if they're on a supported platform and they know the risks, but otherwise processes just work. All of this is to say there are many answers to a problem, and that doesn't mean they're all correct. And it doesn't even mean any of them are correct, for that matter. If you're writing a supervisor-like application like me, consider your target audience. Is what you're doing performance critical? Is it resource constrained in your deployment environment? What platforms do you need to support? Is Unix fine? Do you also need to support Windows? Or maybe you need this to work on platforms like iOS and Android. How much time and effort do you want to sink into this? Do you want something that just works and you don't mind some of the edge cases? Or does it need to, or are you happy committing the time and resources to make it better? If you're not writing a supervisor application, but you wish you were, come and join the Django Tasks project. Come and talk to me about it. It's great. If you are implementing code, which might be run in a timeout, you've got to consider a few things as well. Consider the exceptions you're catching. Do you need to raise base exception or exception? Do you need to catch those? Or could you catch something more specific? You want to fail where it matters. If an API is meant to take 200 milliseconds and it starts taking 10 seconds, it's probably worth knowing about. You don't want to just hang and hope that someone else will solve it. You want native timeouts wherever possible. If there's a timeout, there might be also worth a retry. Is your code idempotent? Will running it a second time make things better or worse? Hopefully better, not worse. If your code raises an exception, is there some state you need to clean up before letting the supervisor take over? The last thing you want is a timeout and some data corruption. When your patience isn't enough, take action. Your code will stop eventually. The least you can do is be prepared for it. Thank you.
Thanks, Jake. That was a super useful talk. Do we have any? I think we've got time for one question. I didn't actually ask if you wanted to take questions.
I'm more than happy to take questions, yes.
So we've got maybe time for one question. Anybody? No? Oh, Russell.
Oh, one down in the bottom.
Oh, no.
Don't get your steps in.
Thanks for the shout-out for iOS and Android at the end, which is +1 from me. You've gone through the issue with the signals was the non-availability on Windows, or at least one of the issues is the non-availability on Windows.
Yeah.
Are there any analogues of that are available on Windows? Like, is there a Windows-specific version of that could be implemented and then wrapped up in another hyper-level API, or is this just something that Windows doesn't have that capability at any level?
Yes, that's a really good question. One of the things I never actually looked into was, obviously, like SIG-alarm is a nice Unix-specific thing, and that's sort of in the signals library bumped in. There are a bunch of Python Win32 APIs that might do similar things. I just haven't had a chance to look at them. I don't actually have a Windows machine to do some poking on, but it's possible, like you say, there are some options that I've listed here. This isn't all of them, and I suspect that there might be something in the Win32 APIs because it is such an important feature of being able to sort of know when an amount of time has passed. So I suspect it's there, and it's not just a gap in the Windows operating system, but it's not something I got a chance to actually poke and investigate as part of doing some of this research. But after this, and with various conversations from people over the last couple of days, there are a bunch of other things I want to look at to sort of make that options list even longer.
Okay, can we give Jake a massive round of applause, please? Thanks very much.